Hi folks! Today we're going to do a Dragonfly Engineering Presents video where we talk about white plastic colorant. We'll talk about formulation, processing, and various applications. For those of you who are familiar with our channel know, we have a couple different white plastic parts, so having a baseline understanding is super helpful to us. In this video, we'll talk about why white looks white. Kind of like why is the sky blue, except for white parts. We'll talk about chemistry that goes into keeping the pigment dispersed, which is really rather important. For those of you who've always wondered about how colorant compounding processes work, we've got something in there for you. And then we'll talk about the nuances in pairing the colorant matrix with a base resin, which is a really key, important role for having nice parts. Dioxide is a critical component to white pigment. I have a ball and stick chemistry model where the red is oxygen and the blue is titanium for titanium oxide. On the left is the rutile phase, and on the right is the anatase phase for comparison. Titanium, the metal, is lightweight and strong material, 0.5 to 0.6% of the Earth's crust, so fairly abundant. The aerospace industry uses it for jet engines, airframes, and spacecraft components because they like the weight to strength ratio. Medical professionals use it for joint replacements, bone screws, and dental implants because it can mimic bone and is biocompatible. The dioxide is used for white pigment in paper, plastics, and paints, which is why we're interested in it today. There are two common phases of dioxide for the white pigment, the rutile and the anatase, as you may have guessed. Actually, the rutile uses less pigment volume to achieve the same degree of whiteness, which is really nice, to use less material to get the same bright power. It actually provides superior weather resistance and UV stability over the anatase phase. The anatase, however, is less abrasive than the rutile, making it preferred for paper and textile manufacturing, where machinery wear is a big issue. Both are photocatalytically active. The crystal structure of anatase makes it more photocatalytically active than the rutile, which is great for self-cleaning services, but really bad for paint lifespan. We'll get more into the differences in refractive index in the next slide. I'm sure you've all seen a prism where you have white light coming in on one side that gets bifurcated into RGB on the other side of the triangle. But if you think about that in reverse, RGB must come together and be mixed to make white light. So for a pigment to look pure white, it must reflect and scatter all wavelengths of visible light. A band gap is a characteristic of a material's specific crystal structure and describes its overall electronic structure. It dictates how the material absorbs, reflects, or transmits light. White light has wavelengths of 700 nanometer in red to 400 nanometer in violet, and which works out to about 1.77 eV and to 3.1 eV in bandgap. Now, because dioxide's bandgap is about 3 eV for the rutile phase, no light is absorbed. Visible light passes right through or scatters and keeps the pigment a pristine white. If a material had a bandgap that was lower than 3 eV, it would absorb some blue or violet light to excite its electrons, and this absorption leaves behind this yellow, orange, or black tint, which is not ideal. Refractive index gives a measure of how fast light travels through a material. Refractive index is actually inversely proportional to the bandgap. So by maintaining the lowest possible bandgap that just clears the visible spectrum at 3 eV, dioxide achieves the highest possible refractive index of any common white material. So why is a high refractive index good? Well, we need to consult Snell's law. So in the picture on the left, we talk about a shell that encapsulates the dioxide. And this shell is usually silica and has a refractive index of 1.46. and our polymer matrix, our plastic, might have a refractive index of 1.5. So according to Snell's law, whenever you have two refractive index materials close together, both in proximity and in refractive index, they tend not to bend light. Light passes through them and maintains the same angle and direction, etc. However, if you have a situation with a high refractive index material next to a low refractive index material, you can have a high contrast boundary, such as with the silica to tioxide. And that boundary scatters and redirects light at a significant angle, which is exactly what you want for pigment. And so that's why having a 3 EV band gap, which gives the highest possible refractive index of 2.7, is the most ideal situation for a white pigment. In the second part of the diagram, we talk about the Goldilocks size of the final particle being the shell and tioxide. If it's too small, at about less than 100 nanometers, you don't scatter the longer wavelengths. And so you have a lot of forward scattering, but not a lot of back scattering. If the particle is too large, say 1,000 nanometers or so, you get a lot of reflection and not any forward scattering. And then the most optimized scenario is 200 to 300 nanometers, where you have all the visible wavelengths scattering equally. And this is the Mie scattering regime. Forward versus reverse scattering. In the forward scattering, you can get more of an opaque or translucent look. Whereas if you have a lot of reflection or back scattering, it's going to have a more mirrored look. In both situations of too small and too large, you would need a lot more pigment, which is not economical because that's expensive. So in the most optimized situation, you have the same amount of forward and back scattering, which gives the least amount of pigment needed. And it gives the good look of coverage with enough of the light coming back to your eye for a pristine color. Tioxide is highly photocatalytic, which is not super ideal for plastics. With a band gap of 3 EV, the tioxide crystal will absorb UV, which has more energy than visible spectra, and then in turn generate free electrons. If there's no encapsulation, these excited electrons react with ambient moisture and oxygen to create highly aggressive free radicals, which can degrade organic material, specifically plastics. With the silica encapsulation in place, photogenerated electrons stay trapped inside the tioxide core and are blocked from interacting with the base resin. Additional issue is that the raw tioxide particles are highly attracted to one another and naturally aggregate into large clumps. When they clump, they behave like massive particles. Instead of having that Goldilocks sweet spot size, this massive particle pushes the pigment into the low opacity geometric regime, where you get a lot of reflected scattering, which is super not ideal. Additionally, we start to need more pigment in order to have similar coverage. Again, not ideal. The silica stabilizes the size of the pigment particle and provides a surface with hydroxyl groups, the OH that you see, that can further be functionalized and tailored to improve dispersion in an organic matrix. I'm going to walk you through all the process steps going from raw tioxide all the way to colored pellet that you add to the base resin before injection molding. For the first step, we'll talk about slurry preparation. The raw tioxide crystalline powder is mixed with water to create a suspension. High shear mixers or wet milling beads break up raw agglomerates down to the optimal 200 to 300 nanometer particle size. Chemical dispersants are added to adjust the pH and impart a surface charge that helps keep the particles floating and separated. Next, for step 2, we'll talk about precipitation and the sol gel process. Active silica precursors, typically sodium silicate or tetraethyl orthosilicate, affectionately known as TiOS, are slowly fed into the heated slurry. The pH of the solution is carefully controlled, usually lowering using an acid. This triggers controlled hydrolysis and condensation. Dissolved silica precipitates directly onto the surface of the tioxide crystals, building a dense, uniform, 2 to 5 nanometer thick, amorphous silica layer. Step 3 will be washing and drying. The encapsulated slurry is filtered to extract the solid particles. The resulting filter cake is washed repeatedly with pure water to strip away any byproducts, salts, etc. that could degrade the plastic properties. The clean cake is dried in a large flash dryer, air milled to break up slough clumps formed during the drying process. In step 4, we do a silane or polyol treatment to the surface. The dry core shell particle is sprayed with an organic surface modifier, typically a silane or a polyol. The organic molecule chemically anchors to the OH hydroxyl group on the silica shell. The outward-facing particle becomes very compatible with organic polymers, allowing the powder to wet easily and compatible with molten plastic. For dry blending, step 5, the functional core shell powder is mixed with a carrier resin, like polyethylene or polypropylene, and processing lubricants. The higher concentrations of pigment are used, typically 50 to 80% of the tioxide powder by weight. In step 6, the dry mix is fed into a co-rotating twin screw extruder, heated above the melting point of the carrier plastic. The shear from the augers forces the individual core shell particles to separate and distribute evenly into the plastic matrix, locking in that ideal scattering configuration. Step 7 is pelletization. The molten composite is pushed through a die into long strands, cooled instantly in a water bath, and chopped into uniform plastic pellets. These concentrated white pellets are shipped to plastic molders who mix them in at 2 to 5% ratio from the raw plastic to color the consumer goods. So I have 2 examples here of white colorant in pelletized form. This one on the left, which I'm going to do a close-up here, is for the universal carrier, the low temperature material. I just put these pellets on blue sticky tape so that you can get better contrast. But you can kind of see what that looks like. They're a little bit bigger in size than the other ones. So these pellets are white pigment in polypropylene matrix. So they're a little smaller. They have a more distinctive surface. You can see the severance action between pellets. The marks left still on the surface. So anyway, just kind of comparing and contrasting and seeing some real-life examples of these. So far, we have focused our discussion on the tioxide particle and particle encapsulation. Next, we're going to take a closer look into the surface functionalization and the interface between the pigment particle and the colorant matrix, as well as the dispersion of the pigment into the matrix. Longer term, we will look at the compatibility with the base resin. Your compounding strategy is basically how to get the silica encapsulated tioxide into your polymer matrix of choice. I'll talk about 3 matrices: EVA, polyethylene, and polypropylene. Choosing the right silica surface treatment depends on the molecular structure of the target plastic matrix. EVA is known as the universal carrier because of its unique dual polarity. The vinyl acetate segments bind well to polar elements, while the ethylene segments blend into polyolefins. So for that strategy, you can treat your silica surface using polyol treatments or short-chain alkali silanes. The processing advantage is that EVA has a low melting point, allowing for gentle processing. Moving on to the polyethylene, this is an entirely nonpolar crystalline material. The strategy for the surface functionalization would be to use long-chain alkaline silanes like octosaline or hexadecylsaline for the surface treatment. Those long-chain hydrocarbons would mimic the polyethylene molecular backbone and help intermix. This would maximize pigment loading efficiencies without causing melt fractures. For the polypropylene, this is a highly sensitive material to viscosity changes and can degrade at higher temperatures. So the strategy for the silica functionalization would be to combine alkosalines with low molecular weight polypropylene wax or functionalize maleic anhydride polypropylene, MAP for short. The maleic anhydride polypropylene would bridge between the silica shell and the bulk polypropylene matrix. This would lower melt viscosity, minimize shear, overall to ensure clean dispersion during injection molding. So let's just pretend for a minute that the functionalization of the silica-coated tioxide particle was forgotten or left out. What would happen then? The silica surface has a polar hydroxyl OH group that would repel the long hydrocarbon chains of the polypropylene matrix. This repulsive dewetting effect would result in a separation or void formation at the silicon polypropylene surface. There would be an increase in processing temperatures, high shear, and pigment clumping. Overall, not a good situation. Let's discuss the steps that are needed for silica surface functionalization with maleic anhydride polypropylene, or MAP for short. First, we'll need to expose the silica to ammonia to functionalize the surface with amines. Next, we'll graft the maleic anhydride polypropylene to the surface amines through ring opening mechanism. After the maleic anhydride polypropylene is fully attached to the surface, the long hydrocarbon tail is able to interact with polypropylene matrix, resulting in uniform dispersion of the pigment particles in the matrix. This comparison outlines the major benefits for using the maleic anhydride polypropylene surface functionalization for tioxide pigment particles in polypropylene matrix. The untreated silica particles agglomerate inside the matrix, resulting in poor dispersion as compared to the pigment particles that have been surface treated with maleic anhydride polypropylene. For the surface treated group on the right, the long hydrocarbon tail of the maleic anhydride polypropylene does not allow the pigment particles to get close enough to touch each other, keeping them well separated. There is good wetting and incorporation of the treated pigment into the polar matrix. We just discussed the importance of using tailored surface treatment to optimize dispersion of white pigment into polypropylene. Unlike polypropylene with its long hydrocarbon chains, ethylene vinyl acetate has both polar and nonpolar groups. Well, that should make ethylene vinyl acetate more compatible with bare silica surface, right? Do we still need to do surface functionalization? Let's see what would happen without any silica surface treatment using EVA or ethylene vinyl acetate as the carrier matrix. The acetate groups, which like to interact with hydroxyl OH groups, are spaced out along the EVA backbone. This gives only partial coverage, in that not all of the OH surface groups will have an acetate group to interact with. The places on the silica surfaces that don't have an acetate group will be free to get close to a neighboring particle and stick to this neighboring particle since the OH groups like each other so much. The particle-to-particle contact will lead to clumps, which isn't good for color dispersion. For an EVA matrix, a polyol surface functionalization can be used on the silica surface. Polyols such as a polyether or modified polyoxyethylene have alternating polar and nonpolar structures, such as a polar backbone alongside a longer, flexible, and less polar segment. Polyol matches the moderate polarity of EVA, giving good steric coverage to the pigment particle while fitting in well with the EVA matrix. This comparison outlines the major benefits for using the polyol surface functionalization. As previously mentioned on the left, in the untreated scenario, the acetate groups would not fully cover the silica surface, and the OH groups would preferentially stick to each other, causing clumping. On the right, using the polyol keeps the silica surface fully covered, and the pigment particles separated. The polyol blends in with the EVA, providing good wetting and incorporation of the treated pigment into the matrix. We have discussed the silica-encapsulated tioxide particle and the importance of surface functionalization as a method to achieve good dispersion of the pigment into the colorant matrix. Next, we're going to assess the compatibility between the colorant matrix and the base resin and how that impacts part quality. So if we want to talk about colorant matrix resin compatibility with base resin, I think it's helpful to stand back for a second and take a look at some of the typical processing temperature and ranges for common plastics. So you have kind of a commodities plastics, which is your polyethylene, your polypropylene, your polystyrene, and ABS. And these guys process 170 to about 280, and they typically have a little bit larger process window than some of the engineering resins. So engineering resins are typically processed higher, 260 and above, and have tighter process windows. So on this graph, we're talking nylon 66 and the polycarbonate. So you can kind of see that if you think about this as two different groups, if you put one of the commodities plastics into one of the engineering plastics, you might have some burning that could happen, or some other process issues, and the reverse is also true, where if you have an engineering plastic and you put it into the commodities group, you might have some issues in processing that. So yeah, I think that's helpful to kind of like see those processing temperatures and kind of think about what that means in terms of compatibility. So in this table, we're looking at base resin crossed against the colorant matrix resin. And green means that you have good compatibility, red means that the compatibility is not great, and yellow is kind of warning or watch out. It's very situational. One thing that stands out in this table is that like on like works. Polyprop and polyethylene, if you have them as a base or the colorant, or vice versa, that works. Similar for the engineering materials, if you have a base resin and a colorant resin that are the same, that also works. For the universal carrier, they do live up to their name, and they're a very versatile option for polyprop, polyethylene, styrenes, and can be situational for the more engineering materials, mostly because of heat, and so that's something to be checked. Whenever we start thinking about putting a polypropylene or polyethylene colorant matrix into higher temperature engineering type plastics, we need to consider that there could be degradation of the polyethylene carriers in those matrices. So that's something to consider, and it highlights in this table. The styrenics are kind of interesting, and they offer a more flexible mid-ground chemistry. The styrenics base resins show the highest tolerance for different carriers, and they only drop to situational for polyolefin and engineering options. So there's clear material hazards and performance risk whenever crossing incompatible chemistries that can trigger severe material degradation. Some of those risks include destroyed optical clarity and reduced impact strength in acrylic. Other mismatches cause severe mixing issues or structural weakness or thermal degradation. So those things are things to watch out for. So if you pick a base resin and a colorant resin that are the same, everything should go well. But let's talk about what happens whenever you pick a high heat base resin and a low heat carrier resin. For this example, we'll consider polyethylene, polypropylene colorant carrier and a polycarbonate base resin. The low surface energy and nonpolar polyethylene or polypropylene hydrocarbon bonds do not bond with the high surface energy polar aromatic polycarbonate groups. This will result in a phase separation because of the lack of interaction between these two types of materials. We also have a thermal problem here because the polyethylene or polypropylene will break down at temperatures well below the 280 C needed to process the polycarbonate. There's also a chain scissor matrix attack that occurs. So If you process at 280C, the polymer chains start to scission the polyethylene carrier, which this starts at about 200C. You get volatile off-gassing of methane and other gaseous stuff. And there's also a chemical chain reaction where the free radicals that come off of the degrading polyethylene will start attacking the polycarbonate matrix, degrading the base polymer structure. The outcome is really not good in that you have aesthetic issues and you're also going to have structural issues. Those trapped gases leave silver splay marks or maybe something like a diesel mark across the molded part. You're going to could get some charring, just depending on how high temperatures you get inside the extrusion and inside the mold. And that's from the unstable carrier. And this could cause black burning and discoloration. You could also get mechanical failure in the form of delamination, like fractured planes, destroying the impact strength and optical clarity. Okay, folks, it's time to sum it up. We discussed why the band gap and reflective index of thioxide makes the best material for white pigment. We covered how white pigment particles are made and why surface functionalization tailored to the use case is important for pigment dispersion in the plastic matrix. We covered thermal and chemical aspects of compatibility between the colorant resin and the base resin, and as well as how these pairing choices can impact part quality. I hope you enjoyed the video. If you are interested in another similar video about different pigment colors, please leave your suggestion in the comment below. Thanks for watching.